So good afternoon, everyone. So today in this session, we'll be starting with the NEET one-shot series, right? We'll be starting with the most expected chapters, and from the most expected chapters, we'll be discussing the most expected questions, right? So the chapter that we'll be discussing first regarding the NEET 2024, we'll be starting with the current electricity, right? There will be two parts of this current electricity chapter. This is the part one. And the part second of this current electricity chapter will be discussed in the next lecture, right? So let's start with the part first of current electricity, right? With respect to the NEET 2024, right? It will be purely discussion based on the questions, right? And through all these questions, each and every concept will be revised, and it will be beneficial for you as well, right? With respect to the practice of the questions, right? We'll be starting with this chapter, that's current electricity, right? Now you can see that the first question here is the current I varies as a function of time, that's 2 plus 4t, right? Where t is in seconds, is flowing through a wire for 2 seconds, right? We have to calculate the amount of charge flown through the wire. The question is that find out the amount of charge flown through the wire, right? So we know that current is defined as the rate of change of charge per unit time, right? Or it is defined as I is equal to TQ over TT, right? Current is defined as TQ over TT, right? Now we have to find the amount of charge flowing through the circuit, right? Or we can write it as IDT will be equal to DQ, right? Now if we integrate on both sides with proper limits, let's suppose from time T1 to T2, right? Then the charge flown will be equal to the delta Q, right? So delta Q will be the amount of charge flown, right? So the amount of charge flown through the circuit will be given by either integral of T1 to T2, right? T1 to T2 IDT, right? If we integrate this current function with respect to time, we'll get the total amount of charge flown, right? Now we have been given that the I is given as 2 plus 4t, right? We'll just plug in the value of current in this equation, 2 plus 4t, right? With the limits through a wire for 2 seconds. It means the limits will be from 0 to 2 seconds, right? We can write it 0 to 2 with integration of 2 plus 4t, right? With respect to time, right? Now this delta Q charge will be equal to, now integrating 2 with respect to t, it will be nothing. It will be 2t, right? With limit 0 to 2, right? Plus the integration of 4t will be 4t square upon 2, right? With the limits 0 to 2, right? Now from here, putting the values of the limits, right? So it will be upper limit minus lower limit. So it will be 4, right? It will be 4. And from here it will be 2 into 2 square, right? That will be equal to 8 plus 4. That will be equal to 12 coulombs, right? It means that 12 coulomb of charge will be flowing through the circuit in a time t equal to 2 seconds, right? So between 0 to 2 seconds, the amount of charge flown through the circuit will be 12 coulombs, right? Now, another method to solve the same question is that we can just solve the same question by the second method using the concept of the graph, right? We can use the area under the curve, right? We know that dq delta q amount of charge flown is nothing. It's integral of IDT, right? IDT with the limits t1 to t2, right? Now this is nothing. This represents the area under current time graph. This is nothing. This is the area under current time graph, right? And that's equal to the charge flown, right? So area under current time graph gives the charge flown, net charge flown, right? In a given time, right? So the area under current time graph will give us the charge flow. Now you can see here the current time graph is a straight line, right? It's a straight line. Whatever area will be enclosed by this current time graph will give us the total charge, right? So there are two ways to solve this question. One way is to integrate the current with respect to the time with the proper limits to calculate the total amount of charge. Another method to solve the same question is to use the graph to calculate the area under the graph so that we can calculate the total amount of charge flown, right? So there are two ways. One way is to integrate the current with respect to time. Another way is to use the concept of area under the graph, right? Area under the graph. So Now, calculating the area under this graph, current time graph, you can see here it's a trapezium, right? And the area of trapezium is nothing. It's given as half of sum of parallel sides, right? Half sum of parallel sides multiplied by the distance between them, right? Multiplied by the distance between them. Multiplied by the distance between them, right? So you can see here the parallel sides are this side and this side is the parallel side, right? You can see the value of this side is 2 and the value of this side is 10, right? So it will be 2 plus 10, right? Multiplied with the distance between them. So the distance between these two parallel sides is this, that's equal to 2. We'll multiply here by 2. 2 and 2 will get cancelled. We'll be left with 10 plus 2. That will be equal to 12 coulombs, right? Now you can see here we get the same answer. We're getting the same answer from the by integrating the current versus time graph, right? By integrating the current with respect to the time and by calculating the area under this current time graph. So it's a very important question, right, with respect to a NEET. So if current as a function of time is given, right, and you are asked to calculate the total charge flown through the circuit, there are two ways. One way is to integrate the current versus current with respect to time with the proper limits, will get the total charge. Another way is that if the current versus time graph is given, then to calculate the total charge flown through the circuit will be given by the area under the current time graph, right? We'll just calculate the area under the current time graph to calculate the total amount of charge flown through the circuit, right? So this was the question number 1. Let's move on to the question number 2, right? Now, with respect to the question number 2, you can see the question on the screen is that on increasing temperature of a conductor, which of the following is correct, right? So if we increase the temperature of a conductor, so which of the following will be correct, or what will happen to the conductor, or what will happen to the different physical quantities, right? So the first option is that relaxation time decreases, right? Drift velocity decreases, conductivity decreases, and resistivity increase. All of the above are correct. Now, we know the relaxation time is the average time between the two successive collisions between the two electrons in a conductor, right? So relaxation time. So upon increasing the temperature, if the temperature is increased, right? If the temperature is increased, so what is going to happen? The thermal energy of the electron will increase. If the thermal energy of the electron will increase, the collision frequency increases, right? Collision frequency increases, right? Collision frequency increases. So if the collision frequency increase, then the relaxation time will decrease, right? Because if the frequency between the successive collisions will increase, it means the time taken between the two collisions will be less, right? It means that the relaxation time tau, that's the relaxation time, it will decrease, right? Relaxation time decreases, right? Now the question is, what will happen to the drift velocity, right? We will see what will happen to the drift velocity. So drift velocity is given by charge of electron multiplied with the electric field, tau upon m, where tau is the relaxation time. Now you can see here, if we decrease the if we increase the temperature, relaxation time decreases. If the relaxation time decreases, right, then the drift velocity will also decrease. It means that relaxation time will decrease, drift velocity will decrease. Now the question is, what will happen to the conductivity? We know that according to the microscopic form of Ohm's law, J is equal to sigma E, right? Where sigma is nothing, it's the conductivity, and it's given by NE square tau upon m, right? Where tau is once again the relaxation time, right? It means that upon increasing the temperature, the relaxation time decreases. If the relaxation time decreases, then the conductivity will also decrease, right? So this option is also correct. This option is also correct, right? C option is also a correct option, because if the conductivity decreases, we know that resistivity is nothing. It's 1 upon conductivity, right? It's 1 upon conductivity. If the conductivity decreases, then it means that the resistivity of the conductor increases. If the resistivity of the conductor increases, right, then conductivity decreases. It means that all the three options are correct. So the best option for this question is all of the above are correct. So this is the best option, right? So here we actually discussed about the function, how actually the drift velocity, relaxation time, conductivity, resistivity of a conductor changes upon increasing or decreasing its temperature, right? So you can see here relaxation time decreases upon increasing the temperature, drift velocity decreases upon increasing the temperature, conductivity decreases upon increasing the temperature, and resistivity increases upon increasing the temperature, right? So these are some of the quantities, right, that will be varying with respect to the temperature, and this will be the behavior of all these quantities upon increasing the temperature, right? Now let's move on to the question number 3, right? The question number 3 is that a current I flows through a uniform wire of diameter d, right? Then the electron drift velocity is v. The same current will flow through a wire of diameter d by 2 made of the same material. The drift velocity of the electrons in second wire is, right? We have to calculate the drift velocity in the second wire. The question says that we know the drift velocity is nothing. Drift velocity for the current versus relation between current and the drift velocity is drift velocity, area of cross section, number density multiplied with the charge of electron, right? So this is the relation between the current flowing through the conductor and the drift velocity, where A is the area of cross section, Vd is the drift velocity, N is the number density, and E is the charge of electron. Now, the question says that a current I flows through a uniform wire of diameter d. Then the electron drift velocity is v. The same current will flow through a wire of diameter d by 2 made of the same material. The drift velocity of the electrons in second wire is. So from here we can see here the drift velocity can be written as it will be current upon area of cross section multiplied with the number density into the charge of electron, right? Now the current is same, right? Current is same, but the area of cross section of the two wires is different, right? Area of cross section for the two wires is different. Since it's made of the same material, so the number density will be same, right? Charge of electron will be same. So the drift velocity here in this case will be proportional to, or we can say it will be inversely proportional to the area of cross section, right? It will be inversely proportional to the area of cross section, right? Now area of cross section is nothing. Area of cross section will be given by pi r square, right? So it will be proportional to 1 upon radius is nothing, it's a half of the diameter, right? So it will be d by 2, right? D by 2. So there will be a factor of 4 here, right? There will be a factor of 4. D by 2 will be d by 4, right? Whole square, right? So drift velocity is actually inversely proportional to the diameter, right? Once again, you can see the drift velocity is inversely proportional to the diameter, right? The drift velocity of the electrons in second wire, right? The first wire was having a drift velocity. If the first wire was having a drift velocity of v1, let's suppose its drift velocity was v1, right? So v1 will be proportional to 4 upon pi d square, right? Pi d square. It will be pi d square, right? Now talking about the second wire, right? Talking about the second wire, the drift velocity will be 4 upon pi diameter. Now the diameter for the second wire is t by 2, right? It will be t by 2 whole square. So it will be proportional to 4 upon pi t square by 4 in the numerator, right? So it means that V2 will be proportional to 16 upon pi d square, right? 16 upon pi d square, right? Now we have to calculate the ratio between these two, right? It means that V2 upon V1 will be equal to 16 upon 4, right? That will be equal to 4. So it means that the drift velocity in the second case will be actually the 4 times the drift velocity in the first wire, right? So the second wire will have a drift velocity 4 times the first wire, right? So this is how we can calculate the relation between the drift velocities of the two different wires, right? Now, let's talk about the question number 4, right? It's a very important question, right? With respect to the current density, we know that current density is defined as according to microscopic form of Ohm's law, that's sigma E, right? Or we define this current density as current per unit perpendicular area, or the current flowing perpendicular to the given area, right? The current density across a cylindrical conductor of radius r varies in magnitude according to the equation J is equal to J naught minus R upon capital R, where R is the distance from the central axis. Thus, the current density is maximum J naught at the axis, right? We can see if we put R equal to capital R, then the current density here will be equal to 0, right? At R equal to 0, right? So, and decreases linearly to 0 at the surface, right? The current in terms of J naught and conductor's cross-sectional area A is. So, we have to calculate the current, right? We have to calculate the current. So the current as a function of radius r. Now we know that current density is defined as or the relation between the current and the current density is nothing. It's integral of J dot dA, right? J dot dA, where current density is a vector and area here is also a vector, right? It's the area vector, right? Now the J is given as the direction of the area vector will be along the direction of current density, so that their dot product will be equal to J into dA, right? It will be J into dA, right? Now the question is that uh, the value of J is given as J naught 1 minus small r upon capital R. Now the dA will be written as 2 pi r into dr, right? 2 pi r into dr. Taking limit from 0 to r, right? We'll integrate it. So J naught will be outside integral, right? J naught 2 pi will be outside integral, right? We'll be left with 0 to r, right? R minus r square upon capital R dr, right? We have to integrate it with respect to r, right? Now integrating it with respect to r, we will get 2 pi J naught, right? 2 pi J naught, 2 pi J naught. So it will be r square upon 2 with the limits 0 to r, right? Minus 1 upon r with the limits r cube upon 3, right? R cube upon 3 with the limits 0 to r, right? So this will be the integration of this equation, right? The current as a function of r will be 2 pi J naught, right? Putting the limits, it will be r square upon 2, right? Minus r cube upon 3r, right? R cube upon 3r. So this will be the current as a function of r, right? This will be the current as a function of r. If we calculate the maximum value or current, the current in terms of J naught and conductor's cross-sectional area A is, right? So it means that if we the cross-sectional area is pi r square, right? The cross-sectional area is pi r square. So we can replace pi r square, right? Pi r square with A. Then accordingly, we'll find the relation between current and area of cross section, right? So this is the current versus or the current as a function of radius r, right? We will to calculate the current from the current density, we'll have to integrate J dot dA, where J is a vector, J is a current density, it is also a vector, area is also a vector, right? We have to integrate it to calculate the current through a given radius, right? Now let's move on to the next question, right? The question number 5 says that two wires each of radius of cross section are, right? We have two wires each of radius of cross section are, but of different materials, right? They're of different materials are connected together and end to end, right? If the densities of charge carriers in the two wires are in the ratio 1:4, right? If the densities of charge carriers in the two wires are in the ratio 1:4, right? The drift velocity of electrons in the two wires will be in the ratio, right? It means that we have to calculate the ratio of the drift velocities between the two wires, right? Ratio of the drift velocities between the two wires. We know that drift velocity is nothing, it's defined as Vd, right? It's equal to E tau upon m, right? E tau upon m, right? So two wires of each of radius of cross section are, but of different materials are connected end to end, right? They're connected end to end in series, right? They're connected end to end in series. If the density of charge carries the two wires are in the ratio 1:4, the drift velocity of currents in the two wires will be in the ratio. If they are connected end to end in series, it means whatever be the current will be flowing in a wire, it will be same for both the wires, right? It will be same for the both the wires, right? And area of cross section should be same for both the wires because they are end to end connected, right? We know the current relation between current and the drift velocity is Vd, current is equal to Vd A and A, right? Now they are end to end connected, right? If they are end to end connected, their area of cross section will be same, right? Their area of cross section will be same, but the current will also be same because they are in connected in series with each other, right? So the amount of current through the both the wires will be same, right? So current I will be flowing through this wire and the current I will be flowing through this wire as well, right? Now the thing that will be different will be the charge density, right? Now you can see here the drift velocity is different and the charge density is different, right? So if the charge density is different, the drift velocity has to be different. So we can write drift velocity in terms of current here, I upon P, I upon ANE, right? I upon ANE. So area of cross section is same, charge is same, current is same, right? So it means that for this case, the drift velocity will be inversely proportional to the current density. It will be inversely proportional to the charge density, not current density, right? So from here we can write Vd1 upon Vd2, right? That will be equal to N2 upon N1, right? N2 upon N1. So we have been given the ratio of the charge densities or the charge carriers as 1:4, right? It means when 1:, N2 is given as 1:4, right? 1:4. Therefore, N2 ratio N1 will be 4:1, right? 4:1. So it means that V1 upon V2 will be nothing. It will be 4:1, right? 4:1. So this will be the ratio of the drift velocities in the two conductors, right? So we have used the same equation, relation between the current and the drift velocity, where current is equal to Vd A and E, where V is the drift velocity, is the area of cross section, N is the number density of the charge carriers, is the charge of electron, right? And I is the current flowing through it, right? So with the help of this equation, we could calculate the ratio between the drift velocities of the two wires, right? Now let's talk about the question number 6, right? You can see here in the question number 6, we have been given I versus current versus voltage graph, right? Current versus voltage graph, right? So in this question, we have been asked to find the R1 ratio R2. So it means that we have the two curves here for the two conductors, right? For the two conductors, we have two curves here, right? Let's suppose for the conductor 1, the resistance is R1, and for the conductor 2, the resistance is R2, right? So for these two conductors, we have to calculate the ratio between the resistance R1 and R2. We know that according to Ohm's law, V upon I is equal to R, right? V upon I is equal to R. So V upon I is nothing. It's a slope of VI graph, right? Slope of VI graph. So the slope of VI graph will give us the resistance, right? It will give us the resistance of the conductor, right? It will give us the resistance of the conductor. So slope of graph is nothing. It's the tan of theta, right? It's the tan of theta. It means the tangent of the what we call as tan of theta, or we can say the angle made by the current versus voltage versus current graph with the x-axis. Tan of that angle will give us the slope, or tan of that angle will give us the resistance of that conductor, right? But the question here is that we have been given as IV characteristics, right? Then the characteristics I upon V will be equal to 1 upon R, right? 1 upon R. So it means that slope of IV graph will give us reciprocal of the resistance. It will give us 1 upon R, right? The slope of IV graph will give us the 1 upon R, right? So the slope of IV graph will give us the 1 upon R, right? But we have to calculate the ratio of the resistances. Right? Now you can see here R1, here for this conductor, right? For the first conductor, 1 upon, since it's a IV graph, so the slope will be slope will give us reciprocal of the resistance. So 1 upon R1 will be tan of 60 degree, and tan of 60 degree is nothing. That's equal to root 3, right? That's equal to root 3. And 1 upon R2 is nothing. That will be tan of 30 degree, right? Tan of 30 degree, right? That will be equal to 1 over. Now calculating the ratio R1 ratio R2, right? We have to calculate the R1 ratio R2, right? That will be equal to R1 ratio R2, right? That will be equal to 1 over root 3, right? Over, it will be 1 over root 3 over root 3, right? It will be 1 over root 3 over root 3, right? So from here it will be 1:3, right? From here it will be 1:3. So this will be the ratio of the resistances between the two graphs. So from this question we concluded that the slope of VI graph will give us the resistance, but the slope of IV graph will give us the reciprocal of the resistance, right? From there we can calculate the resistance. So you have to take care of this thing. Slope of VI graph will give us the resistance, but the slope of IV graph will give us the reciprocal of the resistance, right? So keep this thing in your mind. Now let's move on to the next question. In this question number 7, you can see in the shown VI curve, right? VI curve, which of the following options will be a correct option? So we have three conductors here. We have three conductors. This is conductor 1, this is conductor 2, and this is the conductor 3. So the graph between potential difference and the current for the three conductors has been given, right? It's a straight line passing through the origin. And the resistance for these three conductors is R1, R2, and R3. And we have to find the relation between R1, R2, R3. We have to show uh, which conductor has the larger resistance and which conductor has the less resistance, right? Which conductor has larger resistance and which conductor has the less resistance. And we know that the resistance for VI graph is given by the slope of VI graph, right? Slope of VI graph. So this gives us tan of theta will give here as the resistance, right? It will give us the resistance, right? Right? That's the slope. That's the slope of VI graph, right? Slope of VI graph. Now you can see here the slope of R1 curve is greater than slope of R2 curve than the slope of R3 curve, right? So the slope of R1 is greater than slope of R2 than slope of R3. It means that R1 will be greater than R2 will be greater than R3, right? So R1 will be greater than R2 will be greater than R3, right? So with the help of slope of potential and current graph, we can calculate the resistance, right? Now let's move on to the question number 8, right? Let's move on to the question number 8. In the question number 8, you can see here we have three copper wires having their lengths in the ratio 5 ratio 3 ratio 1 and their masses are in the ratio 1 ratio 3 ratio 5, right? The question is that what will be the ratio of their electrical resistances, right? We have to find the ratio of electrical resistance, right? Now let's look at this question number 8. We know the resistance of a conductor is nothing that's given by rho L upon A, right? It's given by the rho L upon A, where L is the length of the conductor, A is the area of cross section of the conductor, and rho is the constant here, which we call as resistivity of a conductor, right? And the resistivity is the constant. It only depends upon the temperature of the conductor, right? The rest of the resistance only depends upon the length of the conductor and area of cross section of a conductor, right? Now we have to calculate. We have been given the ratio of their lengths, right? We have been given the ratio of their length. That's 5 ratio 3 ratio 1, right? 5 ratio 3 ratio 1. And we have to calculate the ratio of their masses is also given as 1 ratio 3 ratio 5, but we have to calculate the ratio of their resistance, right? Now how we can get a mass term here in this equation? We know that if we multiply here, if this is the conductor, right? If this is the cylindrical conductor, right? Area of cross section A, if this is the cylindrical conductor of area of cross section A and length L, then the volume of this conductor will be given as A into L, right? Area of cross section multiplied by the length, right? Area of cross section multiplied by the length, right? Now if we multiply here with length, right? If we multiply here with length, right? In the denominator and in the numerator as well, right? In the numerator as well, right? So it will be L square in the numerator, it will be L in the denominator, right? So it means that we can write this equation rho L square. A into L is nothing, it's the volume of the conductor. We can replace it with the volume of the conductor. And we know the density, right? Density of a conductor is defined as density D. It's nothing, it's defined as mass per unit volume, right? It's defined as mass per unit volume. So volume can be here replaced with mass per unit density or mass by density, right? Volume here is mass upon density. Now replacing volume from with the density, right? The resistance here will be rho L square upon mass multiplied with the density T, right? So this will be the final equation in terms of the density of a conductor, mass density of the conductor and mass of a conductor, right? Now from here you can see the resistance is nothing, it's proportional to L square upon M, right? It's proportional to the L square upon M, where L is the length of the conductor, M is the mass of conductor, right? This is the length of conductor, this is the length of conductor, right? And M is nothing, it's the mass of conductor, right? It's mass of conductor, right? L is the length of the conductor and M is the mass of conductor. Now we have to calculate the ratio of these resistances. So R1 ratio, R2 ratio, R3 will be nothing. That will be equal to, it will be equal to, so it will be L square upon M, right? It will be L square upon M, right? So their ratio we can calculate, that will be equal to 25, right? So it will be 25 over 1, right? Ratio. 9:3, right? And 5:1, right? 1:5, not 5:1, 1:5, right? So this will be the ratio between the resistances, right? Now, if we multiply in the numerator by a factor of 5, right? To get it in the reduced form, right? If we multiplied numerator by a factor of 5, we'll get here 125, right? And it will be 9:3, we can write it as 3:1 multiplied by 5, that will be 15:1, right? 15:1. So the correct answer for this question will be 125:15:1. It means the option C will be the correct option for this question, right? So this is how we can compare the mass of a conductor, length of a conductor with the resistance, right? So one way is to rho L square upon A is the equation, and from that equation we can derive a relation between the mass of a conductor and resistance of a conductor, right? In terms of length and mass, right? Now let's talk about the percentage change in conductor, right? There are certain questions asked in different exams like JEE and NEET on the percentage change in resistance if the length of the resistance or the length of the conductor is changed, or if the area of cross section of the conductor is changed, right? I will try to see how we can actually calculate the percentage change in resistances, right? Now let's discuss this one by one, right? Now the first case is these formulas are only valid for cases where percentage change in length, comma radius, and area of cross section is less than 5%, right? Is less than 5%. Is less than 5%. We can use this equation. Or even if it is close to 10%, we can still use this equation. But beyond this, beyond 10%, we will not be using these equation for calculation of the percentage change in resistance, right? Percentage change in resistance. So the resistance of a conductor, let's suppose if the length of the if the conductor is stretched, right? If the conductor is stretched, upon stretching, what happens? The length of the conductor increases, right? Then the area of cross section has to decrease, or we can say radius of the conductor has to decrease, right? So upon stretching a conductor, the length of the conductor increases, area of cross section decreases, or the radius of the conductor decreases, right? Now let's suppose the percentage change in resistance of a conductor, right? Resistance in a conductor, it will be given as 2 times delta L upon L into 100, right? 2 times delta L upon L into 100, right? So this is the percentage change in resistance, right? In terms of if the length is changed by some x%, right? If the length of the conductor is changed by x%, uh, then the percentage change in the resistance will be 2 times that, right? So let's suppose if the length of the conductor is changed by x%, then the percentage change in resistance will be twice that of percentage change in the length, right? So it means that it means that if x percentage is the change in the length, right, then the percentage change in resistance will be twice x, right? It will be twice x. Similarly, if area of cross section is changed by some x%, right, then the percentage change in the resistance will be twice delta A, right, upon A multiplied by 100, right? Multiplied by 100, right? So it means if area of cross section is changed by x%, then the percentage change in resistance will be twice x, right? It will be twice x%, right? And similarly, in the third case, if the length, or we can say if the radius of the conductor is changed by, let's suppose x%, right? X%. If it is changed by x%, then the percentage change in resistance will be 4 times the percentage change in radius, right? 4 times the percentage change in radius. It means that if the x% change is there, right? X% change is there in the change in the radius, right, then the percentage change in the resistance of the conductor will be 4 times x, right? It will be 4 times x, right? Now we'll be using these equation, and one of the important relation is that what will happen, how will we calculate the percentage change in the resistance if the percentage change in length or area of cross section or radius of the conductor is greater than 10%, right? For greater than 10%, for greater than 10%, what you will do is that resistance of a length, resistance of a conductor is proportional to L square of the L square, right? Upon stretching, the resistance will be proportional to the L square, right? It means that if the new length of the conductor is made n times of the previous length, then the new resistance will be nothing. It will be n square times L, right? It will be n square times L, right? This will be the new resistance. Similarly, if the radius is changed or decreased by r by n, right? If the radius is decreased by r by n, right? In that case, if the radius is decreased by r by n, right? If new radius of the conductor is becomes r naught by n, then the resistance will become actually n to the power 4 times n to the power 4 times of the original resistance, right? So these are the two important relations to calculate the percentage change in the resistance, or this relation can also be calculated, right? This relation can also be used where we have been given that if the length of the conductor upon stretching becomes n times the original length, then the new resistance will be n square times L. And if the area of, if the resistance, if the radius of the conductor is decreased by r naught by n, then the new resistance will become n to the power 4 times of the original resistance, right? So these are some of the important relations, and these relations should be handy, right? These relation should be handy, right, to calculate the resistance of a conductor, right? Now you can see here we will apply these relations to calculate the resistance of a conductor one by one. So the question here is, a wire is stretched by 30% of its original length. Find percentage increase in resistance. Now you can see here, actually the resistance or the percentage change in length is greater than 10%. It's greater than 10%. And we know that resistance of a conductor in that case upon stretching is proportional to the L square. It is proportional to the L square. It means that the new resistance, if it is the new length is 30% of the original length, right? It's 30% of the original length. It means that L dash will be 1.3 times the original length. Now it means that the new resistance R2 upon R1, that will be equal to L2 upon L1 whole square, right? The value of L2 here is 1.3 times L, right? And the original length here is L whole square. So L at L will get cancelled, right? From here you can see 1.3 whole square, it's nothing, it's 1.69, right? It will be equal to 1.69. So it means that the new resistance here will be equal to R2, that will be 1.69 times the old resistance, right? Now the percentage change will be delta R upon R, right, multiplied by 100. Now delta R is nothing. Delta R is new resistance minus the old resistance, right? Previous resistance, that was R, upon the value R, right? Multiplied by the factor 100, right? So it will be 0.69 into R upon R multiplied by factor 100, right? So it means that there will be a percentage change in resistance equal to 69%, right? The percentage change in the resistance will be 69%, right? 69%. Or you can directly calculate this percentage change as well, right? We know that when the length of the conductor becomes n times, right? If the length of the conductor becomes n times, in that case, new resistance becomes n square times the older resistance, right? Now the factor n here is 1.3, right? 1.3. So the 1.3 whole square is nothing. That's equal to 1.69, right? So we'll just subtract 1 from it. It will be 0.69 and multiply it by 100. So it means that will be 69%. So from here, you can directly say 1.3 whole square, it will be 1.69. It means 69% is going to be the answer, right? 69% will be the percentage change. 69% will be the percentage change in the resistance, right? Now let's talk about the question number 10, right? Let's talk about the question number 10. So in case of question number 10, a wire is stretched so that its radius is decreased by 3%, right? If the radius decreases by the 3%, right, then the percentage change in terms of radius will be delta R upon R multiplied by 100, that will be 4 times delta R upon R multiplied by 100, right? This is the percentage change in the radius. The percentage change in the radius in this question is given as 3%. So it will be 4 multiplied by 3, that's equal to 12%, right? So 12% will be the percentage change in the resistance of this conductor. If the percentage change in the, or if the decrease or the resistance or the radius of this conductor is decreased by 3%, or the percentage change in the radius of this conductor is 3%, right? Then the percentage change in the resistance of this conductor has to be equal to 12%, right? Now, let's move on to the question number 11, right? The length of the conductor is doubled and its radius is halved. Its specific resistance is, right? So the specific resistance is nothing. It's the uh, specific resistance of what we call as resistivity, right? It's the resistivity, right? Resistivity, right? So you can see here, R is equal to rho L upon A, right? Rho L upon A, right? So resistivity is nothing. It's the resistance of a conductor when length of the conductor is of 1 unit and area cross section is equal to 1 unit square, right? So in that case, the resistance will not depend upon the will not depend upon the length of the conductor. It will not depend upon the area cross section, because now the resistance here is specific, right? It's specific to length equal to 1 unit and area cross section to 1 unit square. So in that case, by changing the length of a conductor or radius of the conductor, the specific resistance will not change. The correct answer to this question will be unchanged, right? It will not change, right? It will not change at all. Now let's move on to the question number 12, right? The question number 12 says that a wire of length, let's suppose we have a wire of length L, right? If the wire of length and resistance R is cut into 4 parts, right? Each 3 parts are placed in parallel and 4th part is placed in series with them, right? We have to find the equivalent resistance. It means that we have cut this wire into 4 parts, right? These are 4 parts of this wire, right? Equal parts, right? And if we cut this wire into 4 equal parts, or if we cut a wire of resistance R into n equal parts, then the new resistance of the wire will be nothing. It will be R upon n, because we know the resistance of the conductor is proportional to the length of a conductor, right? If the length becomes 1 by n times, the resistance will become R by n times, right? So R by n will be the resistance of the new conductor, right? So here it has been cut into 4 parts. So the resistance of each part, the resistance of the each part here will be R by 4, right? The resistance of the each part here will be R by 4. Now, from these 4 parts, 3 parts have been placed parallel to each other, right? That means that we have 3 parts which have been placed parallel to each other, right? Like this. 3 parts have been placed parallel to each other, right? 3 parts have been placed parallel to each other, and the 4th part is placed in series with them, right? 4th part is placed in series with them, right? Now the resistance of each part is R upon 4, R upon 4, right? R upon 4, and the resistance of this part is also R upon 4. Now you can see here the 3 parts are parallel to each other, right? So their equivalent resistance will be nothing. It will be R upon 4, right? R upon 4 upon 3, right? It will be R upon 12, right? So this will be the equivalent resistance of these 3 parts. Now R upon 12 will be in series with R upon 4, right? So R by 4, so R by 12 will be in series with R by 4, right? Their equivalent will be nothing. It will be R by 12 plus R by 4, right? That will be equal to 4R by 4, right? 4R by 12, right? That will be equal to R by 3, right? R by 3. So this will be the equivalent resistance of this system, right? If we cut this system into 4 equal parts, right? And place them in this fashion, 3 parts are placed in parallel to each other and 1 part is placed in series with the other 3 parts, right? So this is how we can solve this question, right? With respect to the resistance, right? Now let's move on to the question number 13, right? The question number 13 says that 2 wires of equal diameters of resistivities ρ1, ρ2 and lengths L1 and L2, right, respectively are joined in series. The equivalent resistance of the combination is, right? The question is that we have 2 wires, right? This is wire 1 and this is the wire 2, right? This is the wire 2. The wire 1 has the length L1 and the wire 2 has the length L2. The resistivity of first wire is ρ1 and the resistivity of the second wire is ρ2, right? Now they are joined together, right? If the two wires are joined together, it means that their area of cross section will be same. Let's suppose the area of cross section is equal to A, because they are joined together, their area of cross section has to be same, right? Their area of cross section has to be equal to same. Since these two wires are in series, their equivalent resistance will be nothing. It will be R1 plus R2, right? R1 plus R2, right? And we know the resistance of a conductor is nothing. It's rho L upon A. So it will be rho 1 L1 upon A, right? Plus rho 2 L2 upon A, right? Now let's suppose the equivalent resistance of these conductor is this. This is the equivalent resistor, right? Of area of cross section A, right? And having the equivalent resistivity equal to rho equivalent, right? Rho equivalent, right? Rho equivalent, right? Rho equivalent. And the length of this conductor will be L1 plus L2, right? L1 plus L2. So the R equivalent in this case will be nothing. R equivalent will be rho equivalent, right? Rho equivalent multiplied by the length of this equivalent resistor, that will be L1 plus L2 upon the area of cross section, right? Area of cross section here is A. So it will be equal to rho 1 L1 upon A plus rho 2 L2 upon A, right? L2 upon A. So it means that A and A will get cancelled. We will be left with equivalent resistivity as rho 1 L1 plus rho 2 L2, right? Upon rho L1 plus L2. So this will be the equivalent resistivity of this conductor, right? If they are joined together, right? The equivalent resistivity will be rho 1 L1 plus upon L1 plus L2, right? Now let's move on to the question number 14, right? This is a very important question, right? Very important question, very frequently asked questions, right? Very frequently asked question, right? Uh, for the calculation of the equivalent resistance, right? You can see here, there is a ladder series or infinite ladder network of resistances, right? The resistance of each resistance here is 2 ohm, right? The resistance of each resistance is 2 ohm, right? The resistance of each resistance here is 2 ohm, right? It's a 2 ohm resistance, right? Now it goes to infinity, right? It actually goes to infinity, right? It actually goes to infinity. Now we have to calculate the equivalent resistance, right? We have to calculate the equivalent resistance of this system, right? We have to calculate the equivalent resistance of this system. Now you can see here, after this part, the circuit repeats itself, right? The circuit once again repeats. It's nothing, it's the repetition here, right? It's the repetition. So from this part onwards, the circuit actually repeats itself, right? It repeats itself up to infinity, right? It means whatever be the equivalent resistance of this part, same will be the equivalent resistance of the whole part, right? Same will be the equivalent resistance of whole part, right? It means that if we take this, you can see it goes to infinity. If we take the equivalent resistance of this part equal to R equivalent, then the equivalent resistance of this whole part will also be equal to R equivalent, right? R equivalents. So it means that we can write the circuit in this fashion. This is the resistance, right, of 2 ohm, right? This is the resistor of 2 ohm, right, here. And this is another resistor, right? 2 ohm each. And we have replaced this part of this resistance, right? This part of the circuit with R equivalent, right? With R equivalent, right? With R equivalent. And the equivalent resistance between these 2 points A and B we have to find, right? A and B we have to find. The resistance of this part is 2 ohm, right? The resistance of this part is also 2 ohm, and this part is also 2 ohm. Now the total resistance of this circuit will be, it will be uh, 2 plus 2 plus R equivalent, right? Right? For because these three resistors, this resistor and this resistor, they will be in series, right? It will be equal to 4 plus R equivalent. So finally we'll have the circuit in this fashion, that is 4 plus R equivalent, right? 4 plus R equivalent, right? And 2, right? And it will give us the equivalent resistance that will be also equal to R equivalent, right? And you can see here, these two resistors are actually in series. They are actually in parallel, right? Their equivalent resistance will be 2 times 4 plus R equivalent, right? 4 plus R equivalent upon 6 plus R equivalent, right? 6 plus R equivalent. Now you can see here, what should be the value of this R equivalent such that it satisfies this condition, right? What it satisfies this condition, right? Or we can solve this quadratic equation, right? We can solve this quadratic equation. Let's suppose if we put the value of R1 equal to 1, right? R1 equal to 1. It will be 5 plus 5 multiplied by 2, that will be 10. 10 upon 7, right? If we put the value here 2, it will be 12 upon 8, right? It will be 12 upon 8. 12 upon 8, it will not also satisfy. If we put the value of R equivalent here 3, right? So it will be 3, it will be 7 to the 14, right? It will be 9, 14 upon 9. If we put R equivalent equal to 4, right? It will be 8 into 2, 16, 16 upon 10, right? It will once again not satisfy, right? So what we can do here, we can actually solve the quadratic equation for this, right? We can solve the quadratic equation for this. So the quadratic equation for this will be, it will be R equivalent, it will be R equivalent square, right? It will be R equivalent square, or we can write it R square, right? R square plus 6R, right? 6R, right? R square plus 6R, that will be equal to 8 plus 2R, right? That will be equal to 8 plus 2R. So from here, we will have the values R square plus 4R, right? R square plus 4R minus 8, that will be equal to 0. So this is the quadratic equation. The solution of this quadratic equation will be minus b, right? It will be minus b. So minus b, it will be minus 4 plus minus under root of b square, right? B square is 16 minus 4ac, right? That will be 4 into a c, that is 8, right? Upon 2a, that will be 2 into 1. So it means from here the equivalent resistance for this circuit will be R, that's equal to minus 4 plus, so 8 into 4 will be 32, right? 32, and 32 plus 16 will be 48, right? It will be 48, right? It will be root 48 upon 2. So this will be the final equivalent resistance, right? So the equivalent resistance for this circuit will be here minus 4 plus root 48. We can write it as 4 root 3, right, upon 2, right? So this will be the final resistance for this circuit, right? Minus 4 plus 4 root 3 upon 2 ohm will be the equivalent resistance for this circuit, right? So there are two ways, right? Either we will satisfy this equation with the options, or we can solve this quadratic equation to calculate the exact value of the equivalent resistance, right? We can calculate the exact value of the equivalent resistance by solving this quadratic equation, right? There are two ways. One way is to satisfy this equivalent relation, or another way is to calculate the solution of this quadratic equation, right? Now let's move on to the question number 15, right? Let's move on to the question number 15. The question number 15 says that a uniform wire of resistance 18 ohm, right? A uniform wire of resistance 18 ohm, right? You can see here there is a uniform wire of resistance 18 ohm is bent in the form of a circle. Calculate the effective resistance across the points A and P, right? Once again, a very important question, right? Very important question with respect to your NEET 2024, right? A uniform wire of resistance of 18 ohm, right, is bent in the form of a circle, right? Calculate the effective resistance across the points A and B. Now the total resistance of this circle is 18 ohm, right? 18 ohm. Now this circle is makes an angle of 360 degree at the center, right? 360 degree at the center, right? If it subtends an angle of 60 degree at the center, right, then the resistance between A to B, right, A to B will be, it will be given by 18 ohm is distributed in an angle of 360 degree, right? 360 degree, it means for 1 degree the resistance will be 18 upon 360, and for 60 degree the resistance will be equal to 18 multiplied by 60 upon 360, right? Right? So it will be 6, right? 6 3, right? It means the for 60 degree angle the resistance of this portion between A to B will be actually 3 ohm, right? It will be actually 3 ohm, right? It will be 3 ohm, right? Between A and B, right? Now you can see here, if this part has the resistance equal to 3 ohm, if this part has the resistance equal to 3 ohm, then the remaining part of this circle will have a resistance 15 ohm, right? The remaining part of this circle will have a resistance equal to 15 ohm. The remaining part of this circle will have a resistance equal to 15 ohm, right? And these two parts are actually parallel to each other, right? You can see here, this part of the resistance 3 ohm and 15 ohm are parallel to each other, so their effective resistance will be calculated as, so they are parallel to each other, right? Using the equation of parallel, right? So 3 and 15, so their equivalent resistance will be nothing, it will be 3 multiplied by 15 upon 18, right? Upon 18, right? It will be 3 and it will be 6, right? Or we can write 5 upon 6 ohm will be the correct answer for this question, right? Or this will be the equivalent resistance between A and B for this circle, right? So this is how we can solve this question to calculate the equivalent resistance, right, between points A and B, right? Now let's move on to this question number 16, right? Question number 16. Now you can see here the question number 16 says that if a circuit is short circuited between A and B, then what will be the current supplied by source, right? It means that we have the circuit, right? This is the circuit. This is the circuit here, right? This is the circuit, and this circuit has been short circuited between the 2 points A and B, right? If the circuit has been short circuited between the 2 points A and B, it means if the potential at this point is V, then the potential at this point will also be, right? It means that the potential difference across the points A and B will be VA minus VB, that will be equal to 0, right? If the potential difference between the 2 points is actually 0, it means the current flowing through this portion of this circuit will be equal to 0, because there is no potential difference across points A and B. And if there is no potential difference across the points A and B, it means the current flowing through the through this resistor, and this resistor will be equal to 0. Then the current will be totally flowing through this circuit along this short circuited path, right? This will be the current I, right? This will be the total I current flowing through this circuit, right? And this total current I will be nothing. It will be the total potential difference, that's V, upon the total resistance for this path, that will be 2R, right? That will be 2R. So V upon 2R will be the total current flowing through this circuit, right? The total current flowing through this circuit is nothing, V upon 2R, right? Now let's move on to the question number 17, right? With respect to the short circuiting of a circuit, right? Now you can see here, there is a circuit given. We have to find the equivalent resistance between the points A and B, right? Now in this case, you can see here, these 2 points have been short circuited, right? This point and this point has been short circuited, right? This has been short circuited, right? So it means that if this has been short circuited, right? If this has been short circuited, it means this point and this point will also have the same potential, right? If the potential at this point is V, then the potential at this point will also be V. It means the potential difference across this resistor will be equal to 0, or we can say the current flowing through this resistor will be equal to 0, right? It will be equal to 0. It means that we can remove this resistor from the circuit, right? We can remove this resistor from the circuit because the current flowing through this is actually 0, right? And you can see here this resistor is also short circuited, right? If the potential here is V, here the potential will also be V, and at this point the potential will be once again V. So the potential difference through this resistor is once again 0, right? But the current through this will be 0. So we can remove these two resistors, right? So the two resistors through which the current is 0, is this one and this one, right? So it means that we can remove these two resistors. We'll be left with the circuit as this is the resistor, right? And we'll be left with this resistor, right? Only. So this has the resistance R, this has the resistance R, right? Now you can see these two resistors are parallel to each other, right? Their equivalent will be nothing, it will be R upon 2, right? They will be in series with this R resistor, right? So the R equivalent for this circuit will be nothing, it will be R upon 2 plus R, that's equal to 3R upon 2, right? 3R upon 2 will be the R equivalent or equivalent resistor for this circuit, right? So this was the concept of the short circuiting of how actually short circuiting plays a role. So in short circuits, what happens is that through the short points, the whole current flows through the short line, right? And the potential between the 2 points which has been short becomes equal, and the current flowing, you can see here that whole of the current will be flowing through this path, right? Whole of the current will be flowing through this path because A and B has been short circuited. The potential of A will become equal to the potential of B, or we can say the potential difference between A and B is actually 0. If the potential difference between A and B is 0, it means that the current flowing through this path, through this portion will be equal to 0, right? Or we can remove this circuit, right? We can remove this portion of the circuit, right? That's the reason we get the total current equal to V upon 2R, right? V upon 2R. Now let's discuss few more questions, right? Let's discuss few more questions. Now you can see here the resistance of a tungsten wire at 150 degrees centigrade is 133 ohm. Its resistance temperature coefficient is 0.0045 per degree centigrade. The resistance of this wire at 500 degrees centigrade is. Now we know that For a conductor, right? For an ohmic conductor, right? The resistance of the conductor actually increases upon increasing the temperature, right? Upon increasing the temperature, right? So the resistance of the conductor increases upon increasing the temperature. The relation between the resistance and the temperature is R is equal to R naught multiplied by 1 plus alpha delta T, right? Alpha delta T. Here alpha is nothing, it's the temperature coefficient of the resistance, right? It's the temperature coefficient of resistance, right? Temperature coefficient of resistance. It's the temperature coefficient of resistance, or we define it as it's the relative change in resistance per degree rise in the temperature, right? That's delta R upon R naught multiplied by delta T, right? So for conductors, the resistance actually increases upon increasing the temperature, right? If resistances increase upon increasing the temperature, it means that delta R will be positive. If delta R is positive, it means that the temperature coefficient will be positive for conductors, right? Alpha will be positive for conductors, right? It's a very important point, right? Alpha will be positive for conductors, but same alpha will be negative for semiconductors, right? It will be negative for semiconductors. It means for semiconductors, the value of resistance actually decreases upon increasing the temperature, right? So we have to calculate the resistance of this wire, right, at 500 degrees centigrade. So the new resistance will be the old resistance, that's R naught, that's given as 133, right? 1 plus alpha is given as 0.0045, right, multiplied by the delta T, right? So the delta T is 500 minus 150, right? That will be 350, right? You just multiply this, right? Multiply this these two factors, you will get the new resistance, right? We'll get the new resistance of this conductor, right? We'll get the new resistance of this conductor. Now let's move on to the question. Let's move on to the question. Let's move on to the question number 19, right? Let's move on to the question number 19. The question number 19 says that the lowest resistance which can be obtained connecting 10 resistors, each having resistance 1 by 10 ohm is, right? Now, you know that in case of series and parallel combination, the total resistance in case of series combination, it's given by the sum of each of the resistance, right? In case of series combination, right? If we have n number of resistors, right? This is R1, this is R2, this is R3, right? So the total equivalent resistance for series combination will be nothing. It will be R1 plus R2 plus R3, right? 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 The resistance will be maximum, right? In this case, in series combination, the resistance will be maximum, right? But in case of parallel combination, right? In case of parallel combination, if we have resistances, right? Like this, three resistances in series, R1, R2, and R3, right? We have three resistances in series, R1, R2, and R3. They are in series, they are in parallel, right? And their equivalent resistance will be 1 upon R equivalent, right? 1 upon R equivalent, that is 1 upon R1 plus 1 upon R2, right? Plus 1 upon R3. Now we know that in case of parallel resistances, the equivalent resistance is always less than the smallest resistor, right? It's always less than the smaller resistor. So in case of parallel combination, the equivalent resistance actually reduces, right? It decreases, right? In case of series combination, the total resistance of the circuit actually increases, but in case of parallel combination, the total resistance of the circuit actually decreases, right? In case of parallel combination, right? And it is always less than the smaller resistor or smallest resistor in case of parallel combination, right? Now, in the same way, we have been given the question right here. The question here is the lowest resistance which can be obtained by connecting 10 resistors, right? 10 resistors, right? Having resistance 1 by 10 ohm, right? If n number of resistors are connected in parallel, then the equivalent resistance, each of resistance R, then their equivalent resistance will be R upon N, right? So their equivalent resistance will be R upon N, right? So can the minimum or the lowest resistance for them will be actually obtained by placing them in parallel, right? By placing them in parallel, we have to place them in parallel, right? Place them in parallel. If we place them in parallel, we'll obtain the minimum resistance for the circuit, right? So there are 10 resistors in a parallel, right? Each of resistance R, their equivalent resistance will be, this will be the least resistance, that will be 1 by 10 upon 10, that will be equal to 1 upon 100, right? 1 upon 100. It means that least resistance for this circuit, for this combination, will be 1 upon 100, right? So they will be placed in parallel, right? They will be placed in parallel to each other, right? They will be placed parallel to each other so that the resistance between them is smallest, right? Resistance between them is smallest. That is 1 by 10 ohm each. So this is the equivalent resistance for this circuit for this question number 19, right? Now let's move on to the next question. Now let's discuss about the question number 20. The question number 20 says that a battery of EMF 10 volt is connected to resistance as shown in figure, right? You can see here we have a battery of 10 volts connected for this circuit, right? Connected for this circuit. In this figure, the potential difference between between A and B is, right? We have 2 points here. You can see in this circuit we have 2 points. Point A, this is point A, and this is point B. We have to calculate the potential difference between the 2 points in this circuit, right? We have to calculate the potential difference between the 2 points in this circuit, right? Now, how will you calculate the potential difference, right? Now, let's suppose, let's find the current through. Let's try to find the current along this, right? Along this branch. Let's try to find the current through the two branches of the circuit, right? Through the two branches of the circuit. Let's try to find the current through the two branches of the circuit. The equivalent resistance of this circuit will be these two resistors will be in series. That will be 3 plus 1, that's 4, and this will be 3 plus 1, that will be 4. This will give 4 equivalent resistance, and these two will have a resistance equal to 4 ohm, right? So finally we will have the circuit, the equivalent circuit will be like this, right? It will be 3 ohm resistor, right? 3 ohm resistor, right? And here it will be 4 ohm resistor, right? This is again a 4 ohm resistor, right? This is 4, this is 4, right? This is 3, right? And we have connected a battery of 10 volts, right? Battery of 10 volts here. Now the equivalent of 4 and 4 will be 4 upon 2, right? It will be 4 upon 2 because they are in parallel. It will be 2 ohm, right? It will be 2 ohm, right? 2 ohm. Now you can see the equivalent circuit here. This is the 2 ohm resistor, right? This is 2 ohm, this is 3 ohm, right? The battery we have 10 volts, right? We have 10 volts. So the total resistance will be 5 ohm, right? Or the current through this battery will be equal to, current through this battery will be equal to I, right? That's I current flowing through this battery. That's 10 upon 5, right? That's 10 upon 5, right? That's 2 amperes, right? 2 amperes, right? So 2 ampere will be the current, right? So 2 ampere will be the current through this circuit, right? If the 2 ampere is the current flowing through this circuit, right? Then this current will pass through the battery, that's equal to 2 ampere, right? 2 ampere, and this current will reach at this junction point and it will be distributed along this branch and this branch, and both the branches are having the resistance 4 ohm each. It means the 1 ampere will flow through this branch and the 1 ampere will flow through this branch, right? And the current, let's suppose this is the point C, right? Then the potential difference between C and A will be VC minus VA, right? That will be given as the current flowing through this 1 ohm resistor, that's 1 ampere, right? Multiplied with the resistance, right? That's 1 volt, right? Similarly, VC minus VB here in this case will be equal to the current flowing here is, the current flowing here is 1 ampere, that's 1 ampere multiplied by resistance, that's 3, that will be 3 volt, right? Now what we have to calculate the value of VA minus VB, right? This is the equation first, this is the equation second. Now subtracting second and first equation, we'll get VC minus VB minus VC plus VA, right? Plus VA, that will be equal to 3 minus 1, that will be equal to 2 volts, right? Now you can see here VC and VC will get cancelled, will be left with VA minus VB, right? VA minus VB, that's nothing, that's equal to 2 volt. So it means the potential difference between the 2 points VA and VB, points A and B here is nothing, that's equal to 2 volts, right? Now let's move on to this question, right? The final question here. The three equal resistors, each equal to R, right, are connected as shown in figure, right? And the equivalent resistance between points A and B is. Now you can see here, these are the three resistors, and we have the, the resistors have been short circuited in this fashion, right? It means the potential of this point and this point will be same, right? And the potential of this point and this point will be same, right? It means all the three resistors will be parallel to each other, right? They will be parallel to each other. So it means that we can place these resistors in parallel to each other, right? In this fashion, right? In this fashion, they'll be parallel to each other, right? Each of resistance R, R and R, right? R and R, right? Their equivalent resistance will be nothing. It will be given by R upon N, right? Because each resistor is equal to R, right? That the value of N is equal to 3 because there are 3 resistors. So the equivalent resistance will be R upon 3, right? So R upon 3 will be the total resistance or the equivalent resistance for this circuit, right? Now let's move on to the another question, right? This will be the final question for this session, right? The next part of this session will be done in the next lecture, right? Next part of current electricity will be done in the next section, and in the next session we'll be dealing with uh, Kirchhoff's law, right? Question based on the Kirchhoff's law and power consumption and series and parallel combination of bulbs and cells, right? The current from a battery in circuit diagram shown is, right? You can see here we have a circuit diagram. We have to find out the current drawn by the battery, right? Current drawn by the battery. Now, the current drawn, let's suppose the current drawn by the battery is I. So the current I will be nothing. It will be equal to the EMF supplied by the battery upon the equivalent resistance, right? Now calculating the equivalent resistance for this circuit, you can see here these three resistors are in series, right? That is 7 ohm, 1 ohm and 10 ohm. This will give us 18 ohm, right? 18 ohm equivalent resistance, right? So we can write its equivalent resistance or equivalent circuit like this. That is 0.5 ohm, right? This is 2 ohm resistor, right? And this is 6 ohm resistor here, right? 6 ohm. This is 2 ohm, right? That's 15-volt battery, right? This is 0.5 ohm battery resistor, right? This is 8 ohm, right? They're connected in parallel with this 18 ohm resistor, right? In parallel with this 18 ohm resistor, right? Now you can see here 18 ohm and 6 ohm are in parallel to each other. So their equivalent will be 16 multiplied by 18 upon 24, right? It will be 6, 4, right? That will be equal to 9 upon 2, right? It will be equal to 9 upon 2, right? So 9 upon 2 is nothing. That's 4.5, right? So it means that this circuit can be replaced by a resistance of 4 ohm, right? 4.5 ohm, right? 4.5 ohm. Now 4.5 plus 0.5 is 5. 5 plus 2 is 7 and 7 plus 8 is 15, right? That's equal to 15 ohm, right? So R equivalent is nothing. That's equal to 15 ohm, right? For this circuit, right? If R equivalent is 15 ohm, then the current through this circuit or the total current, net current through this circuit will be flowing. That's equal to 15 upon R equivalent, that's 15. That will be equal to 1 ampere, right? Means the current from the battery in the circuit is equal to 1 ampere, right? So 1 ampere current will be flowing through the battery in the circuit, right? So 1 ampere will be the current here, right? So that's it for today, right? If we had to calculate the potential drops across different, if 1 ampere is current flowing, so 2 volt will be here, right? Potential difference, 2 volt potential difference will be across it, and 0.5 volt will be potential difference across this, and 8 volt potential difference will be across this, and rest of the potential difference will be across 6 ohm, right? So that's it for today, right? So next part of this chapter, that's current electricity part 2, will be done in the next section, right? We'll stop here. Till then, take care and goodbye.